Hey, ladies and gents, welcome back. Hopefully, you're ready to go. I got my coffee, so I know I am ready to go. We will be using both Agile Mind online as well as your workbook. In your workbook, wow, we'll be starting on page 269. We are on lesson 5 in topic 22, page 269, and online. And I realize you're watching this video and you're trying to work online. Remember, pause me. You can pause me. It's probably something you wish you could do during regular school sometimes, but pause me, and that way you can flip back and forth. If you know how to split your screen, that could be helpful too. But otherwise, feel free to pause me. But online on Agile Mind, once you log in, you're going to go to My Courses on the top left side. You are going to, again, look for Unit 8 on quadratics. Topic 22, hit that down arrow. Next to lessons, hit that down arrow, and we are in lesson 5. So Unit 8, down arrow next to 22, down arrow next to lessons, and we are in 5. Now we are going to go ahead and go through this opener. However, I'm going to switch around my computer and I am going to do the opener in my workbook right along with you. So give me a second to go ahead and flip that around. Here we go. So everything we've done, we've been talking about these things called quadratics. And again, what does it mean? Hopefully you can see that pretty decently. What does it mean to be quadratic? We know to be a quadratic, we have to have a highest exponent of 2. Simply put, that's really it. That is the only requirement. That is the most basic quadratic you're going to have. The shape of that graph, if you type this into your calculator, whether you use Desmos, which is that calculator available in Agile Mind, or hopefully you've gone through the instructions and been able to get the calculator on your school computer. But if you type this in y equals, you are going to get this U shape. You are going to get a parabola. Now that parabola, if you graph y equals x squared specifically, that parabola is going to have a vertex, that turning point right here at the origin at 0, 0. It's going to be opening up. And I guess you wouldn't call it wide or skinny. It's just the normal. We refer to it a lot of times, you'll hear later on, as the parent function. So now with these parabolas, with these quadratic functions, we've talked about how do I flip this parabola over? How do I make it wider or skinnier? And that is all based on this a value in front of x squared. That a, we said, if it's negative, our parabola is going to open downward. It's going to flip over. That a also controls how fat or skinny our parabola happens to be. Again, go back to that analogy of working out. If this number in front is a 2, 3, 4, 5, 6, anything bigger than 1, if I work out 5 times as much as I do now, 12 and a half times as much as I do now, I'm going to get skinnier. A number bigger than 1 up here, ignore any negative if there's a negative with that number. Like if it was -7, that negative is going to flip you over, but that 7 is going to make you skinnier. If I had a half, a 0.3, a 0.25, if I work out 0.25 times as much as I do now, I'm going to get wider. So that a value controls the flip, open up or down. It controls wide or narrow or skinny. We've also talked about what makes our parabola shift up and down. We've realized that axis of symmetry, that line right down the middle through the vertex, so far has always stayed right here on the y-axis, but I've been able to move my vertex up. I've been able to move it down. And that was adding dependent on what was behind that x squared. We referred to it as a k. If I added, my vertex went up. If I subtracted, my vertex went down. So let's analyze this. Some of you may be thinking, oh gosh, quadratics, I'm never going to see those in real life. I'm never going to use them in real life. Well, I'll be honest. Many of you may not stop what you're doing where you are and say, hey, this is a quadratic. Let me write an equation. However, quadratic equations can model so many things that you see in real life. And we're going to look at one example right now, but our next lesson next week, we'll be talking about more quadratics you see in real life. If you've ever been to McDonald's, I promise you, you've seen quadratics. So anyway, this one represents data from Jose's soccer kick. A quadratic function can be used to model the data from his kick. So if I think about the x-axis is time and the y-axis is height of his soccer kick, at 0 seconds, this looks like the ball is at a height of 0 meters. He kicks it. Time is passing, so I'm moving slowly to the right, and my soccer ball is going higher. At some point, any ball you kick, throw, whatever it happens to be, time's going to pass. So again, moving to the right, but at some point it's going to reach its maximum value and it's going to start coming back down, forming this parabola or this U shape. Anytime you kick, throw, hit a ball, quadratic can model its path. So first question, I'm sorry, this is going to cover up the graph. I'm going to try and go back and forth. What is the vertex of the graph? Actually, you know what? I'm going to challenge you. Pause my video. Pause the video. See if you can answer questions 1 through 5 pertaining to this graph of Jose's soccer kick. If you can successfully answer questions 1 through 5, you know that you are catching on to what we have been talking about in the last few videos. So go ahead and pause it and answer 1 through 5. Okay, now that we've answered 1 through 5, or you've answered 1 through 5, where's the vertex of the graph? Well, that vertex is that turning point, and I would approximate these coordinates to be 1 over 5 up. And in the context of the situation, meaning use the labels, what does this mean? Well, 1 is my x value, which is time, so at 1 second, and our y value is height in meters. The soccer ball is at 5 meters. At 5 meters. Does this function, so does this equation, does this graph have a maximum or minimum value? Well, remember we said maximum means highest point, minimum being lowest. Well, I can say this definitely has a maximum value. The highest it goes is at a y value of 5. The highest the soccer ball goes is a y value of 5 meters. So what transformations on this quadratic function have you worked on so far? So how is this different than this parent function, this basic parabola we wrote up and drew up in the top right corner? Well, 1, it's flipped. It opens down. We've talked about that. I would say that this one is most likely skinnier or narrower than the normal graph. Also, I would say the vertex has moved up. Now, I'm going to skip down quickly to number 5, because you may be saying, well, not only did this flip over, not only did it get skinnier, which I realize that one's a little hard to see. Don't worry about that so far. But you should see that it flipped over and the vertex moved up. But many of you may be saying, hey, that vertex moved to the right. Are there any other transformations you need to perform? Yeah, our vertex needs to shift or move. Shifts right. And that's going to be something we explore here really shortly. So back to number 4, how can you use these transformations to transform the graph of x squared to model this data? Describe the transformations you used. We already did. We would have to have I can put it in equation form. We would have to have a negative a value. And we know that a value, if I'm going to get skinnier, would have to be something like 2, 3, 4, anything greater than 1. And we also know that for my vertex to move up, I am going to need a k value. And in this case, we know specifically what our k needs to be. We know that we have moved up to 5, so I know that that k is going to be 5. So my equation could be something to the effect of negative, let's go with a 2, x squared plus 5. But the thing that we're missing is, how do we shift this to the right? And again, that's going to be the exploration that we look at today. So I'm going to flip my computer back over. Hi, this is the right there. And on your Agile Mind, hit or hover over those 3 dotted lines, and we are going to go to page 3. And this will help us explore how does a graph of a parabola move left and right. And in answering that and exploring that, we are going to answer on the same page 269, we are going to answer questions 1, 2, and 3. So once you are on page 3 on Agile Mind, I want you to hover over that 2 on the bottom and go ahead and click on it. This gives us, and I'm going to use this square, expands this whole thing. So we have a bigger picture here. It gives us this little slider, which makes it nice and easy to explore. What does this H do? We've talked about an A, which would have been in front of this x squared, so in front of the parentheses. We've talked about K, which comes after the squaring, our new letter, and yes, this is the last transformation, yay. Our new letter is H. So we're going to explore what happens with H. So our first question in our workbook is, how does the graph compare when H is positive? So to move it to a positive numbers are 1, 2, 3, 4. So I'm going to slide to the right. Uh-oh, that's probably not what you expected. Notice I've slid over to a positive 3.5, and the graph is the red one. You notice is the one that's moving. I'm going to slide it back down to 2, positive 2. That red graph, is probably not where you expected it to go. My guess is most of you were thinking, oh, if I add, I'm going to move to the right, kind of like adding after the x squared, or k, adding a k value moved me up. But not in this case. I'm going to slide this as far as it will go, all the way over to 5. And I'm going to fill in, and my answer key will be in PDF form on Canvas, so you can see this later. But answering number 1, what happens when H is positive? My graph shifts to the left, shifts left. You could even say not just the graph, but the vertex is really what we focus on when we are moving left and right or up and down. The vertex shifted to the left when we added, and I'm going to actually highlight that positive in my workbook. My graph shifted to the left. So I'm going to reset this at 0. And now you're going to probably make a really good assumption of what's going to happen. Question 2, what happens when the graph is negative? And I'm underlining negative in my book before I even write any answers. Now notice you can see I am at negative 0.8, negative 2, negative 4.5, minus 4.5, and my graph has moved to the right. And I'm going to be more specific. I'm going to say not just my graph, yes, my whole graph goes, but my vertex shifts to the right when I have a negative, shifts right. Always focusing on the vertex for how we make some movements. Okay, so this one's a little backwards again. K, adding or subtracting a number on the outside made sense. Add, you go up. Subtract, you go down. But I always remember what's on the inside is backwards from what you think. I'm going to shift this again. Notice when I have a positive, when I'm adding, I shift to the left. And when I am a negative, which turns this to subtracting, I'm shifting to the right. Inside those parentheses is always opposite. So answering question 3. Now notice this. How does the graph of x minus h squared compare to the graph of x squared? Well, you know what? Actually, I will flip this around so you can see it now. Again, my PDF, if you want to see any of this in more detail, is available on Canvas. But how does the graph of x minus h squared compare to the graph of just x squared? Notice no h here, meaning I haven't moved left or right. So if h is positive, we shift, remember, backwards than what we think it's going to be. We shift left. Or I should say, if it is a plus h, we shift to the left. And if it says minus h, yeah, we'll rewrite it like that. If I read this as x plus h, we shift to the left. And if I read this as x minus h, we are going to shift to the right. Inside is always backwards from what you think it's going to be. I don't know, I put so much space in there. So we're going to continue to explore that. And in doing so, we are going to flip the page to page 270. We are going to flip the page to 270, and we are going to pop down to number 6. We are going to pop down to number 6. Actually, you know what? Sorry for the back and forth, but I'm going to go ahead and leave this here. You may be thinking, this is a lot of transformations. Now, there's good news and bad news in that. Yes, this is a lot of transformations. A, what flips you over makes you wider or narrower. K, what moves you up and down. And H, what moves you left and right. It is a lot, but the good news is, as you move into geometry next year and Algebra 2 the following year, you're going to be exposed and learn about more shapes that you're going to graph. You're going to see these S curves and these sharp V's, which you've actually seen a little bit. You're going to see tons of different shapes. But the cool news is all of those functions are going to move the same way. regardless if this is squared or if this is cubed or you have absolute value in here or you have square roots, regardless of what it is, if you add or subtract at the end after the exponent, you're going to move up or down. If you have a number in front, that's going to be your fat, skinny flip over. If you have a number on the inside, that's going to be your left and right always. So once you get used to it with quadratics, you're just going to keep seeing that same thing repeat every single year after this. Now, as far as a parabola is called, or as far as a quadratic is called, we call this transformation form, we call it vertex form of the equation of a parabola, and you'll see why shortly right here. You'll see why very shortly. And I'm just going to make some notes in here. A is my flip, and it is also my wide skinny. H is my left right. And K is my up down, just to have it all in one place. And you know what, make some more notes. Up is plus K, down is minus K. Left, remember, inside is backwards. Left is plus K, or excuse me, plus H. Right is minus H. Remember, those signs are backwards than what you think they are. Flip would be a negative. Wide is greater than 1, and skinnier is less than 1, and a value less than 1, but greater than 0. So those are your fractions. I realize it's a little hard to read, but remember, you can always go back in this topic and see more details about all those transformations. Sorry, coffee break. So why is this called vertex form? Well, let's take a look at number 7. What are the coordinates of the vertex of this graph? Well, the vertex is where I stop going down and start going up, or where I change directions. It could be where I stop going up and start going down. My vertex has the coordinates, and I always go left and right first, -3 over 2 up. You may be thinking, but that's only the first line up. We'll take a look at the scale. That happens to be 2. Okay. Let's write this equation. Let's take a look at this equation. Okay, y equals, I'm going to write this all out, a x minus h squared plus k. Let's go with the easy one first, k. How many up and down have we gone? Well, we have gone up, so plus, we have gone up to 2. So I'm going to put plus 2. Working backwards, H. Shift this down so you can see a little bit better. H is my left and right. I have gone to the left, therefore it is a plus. Remember again, inside left and right is backwards from what you think it's going to be. I have gone to the left plus 3 units. And last but not least, A. Is my graph wider? Is my graph skinnier? Now, I can tell you that this graph is actually wider. I know that from looking. One really quick, easy way you can tell is if my graph is not wider, not skinnier, it's just normal, if you will, then from that vertex, if I'm not wider or skinnier, just normal, my next 2 points would be up 1 and over 1 in both the left and right hand direction, where those little X's are. If I'm not wider or skinnier, my next point should make this perfect little triangle with the vertex. I can tell that my graph is outside of that. It's wider. So really, to be quite honest, I'm going to let you just make a guess at what that number is going to be. This is not significantly wider than what is normal, because again, normal would make this perfect triangle with where the X's are, that first line up 1 and over 1 in both directions. So I know wider means that I would have to have a number like a half or a third. If I work out half as much, I'm going to get wider. So I know I'm not significantly wider, so I'm just going to go with something easy like a half. If you are interested, feel free to let me know, and I can teach you and talk to you about how you figure out what that number is exactly. But for right now, as long as you can identify that it's wider, again, if you make that perfect triangle, that's what it should be if it's normal. But if you can identify that it's wider or skinnier and choose an appropriate value, fractions make you fatter, as one teacher said, then as long as you can identify the appropriate type of value, I'm okay if it's not exact. But if you want to know how to make that exact value, please, please, please let me know. Okay, So then we are actually going to move on. I want you to flip to page 272, and we are just going to explore some equations and their graphs and put it all together. So to help you out on Agile Mind, if you hover over those dotted lines and go to number 5, this would help out tremendously. Side note, if when you are working on your assignment for this day's lesson, this could help you tremendously, because you will notice you have a slider for A, you have a slider for K, and you have a slider for H. So while you're trying to figure out transformations and is my graph correct, this will help you tremendously. So I am actually going to no, we'll leave it exactly where it was. A of 1 is my default, and there is a K and an H. So really what this is wanting us to do is match up this graph to what is, actually flip back to page 271 in your work. Where is this on 271? No, let's see. Yeah, you know what? This one is great. Sorry. I'd re-record if I could, but I've already written all over your book. So this one is great if you can just focus on the solid line. This dotted line is actually from number 4 on page 270 in your book, trying to get you to match up those graphs. You're welcome to do that. But like I said previously, I want to focus on page 272, and we are going to see if we can get these graphs on page 272 graphed. If it helps you to just adjust the sliders on this page, paying attention to the solid line, then do that, please. If you would rather use the Desmos calculator right here to help you out, please do that. And if you got that calculator in your on your computer activated, you can use that as well. I'm going to flip this computer around, and I'm not going to use a calculator at all. The greatest part about knowing these transformations, as much as we love the calculator, we know the calculator can be time consuming. So the cool part is, if you know the transformations, you don't need a calculator. You'll automatically know what the graph is. So I'm going to write out our general vertex form, and I call it general only because I'm leaving it as A, H, and K. Once I start putting numbers in, then it's specific, but with just letters representing all the transformations, it's general. Now do note that in general vertex form, this is a minus and this one is a plus. And I guess I didn't talk about this. Why is this called vertex form? Sorry, I'm not doing so good. Why is this called vertex form? Well, take a look at this equation we wrote on page 270. I can see my vertex right here. My K value is always the Y value from my vertex. And my H value, now again, backward signs, my H value is always the X for my vertex. Those vertex coordinates are always visible in vertex form. Again, sorry, I'm a little all over the place. So here we go. We're going to do a couple examples between 272 and 273, and then I'm going to let you ask me questions later today if you need to, and then I'm going to let you get to work. So here we go. Taking a look at A, what transformations do we notice? Well, by placement, that 4 is in parentheses, so it has to be H. So I know that this graph is going to move left and right. H is my left and right. If I have plus H, that is going to be to the left. And if I have a minus H, I am going to be to the right. Well, I see that this is a minus 4. Therefore, this graph is going to move to the right 4 units. So I'm going to take my vertex as normally here at the origin. If I haven't moved anything around, I'm going to move to the right 4. 1, 2, 3, 4. And I'm going to place a dot. And I'll make a note, right 4. I'll just use an R. I have no A value. I have no K value. So I know I'm done. And again, if you go with my little explanation of wide skinny from before, with no wide skinny, I know my next 2 points should be up 1 and over 1 in both directions, and that can help kind of guide what your parabola should look like. If you want to type this into any of your calculators to verify, please do. So then we're going to fill in the blanks. This function represented by this graph, does it have a max or a minimum? Well, it has a lowest point right there, so it has a minimum. And what Y value does it have a minimum at? Well, it doesn't go down to -1, 2, 3. There would be -3. It doesn't go to -2. It doesn't go to -1. It's at 0. It has a minimum of 0. Now, just as a reminder, it's been a while since we've talked about domain and range. Domain refers to the X values on my graph, and range refers to the Y values on my graph. So what X values are on my graph? Okay, well, I don't really see an X value of 1 being crossed, but think about what these arrows do. They're going up, but they're also very, very slowly going out. If I put my pen on there, I can see that my pen is still going off to the left. So eventually I'm going to cross 1. Eventually I'm going to cross 0. And if my paper were large enough, I would keep going to the left. Similarly, if I went off to the right, eventually I'm going to cross 5, 6, 7, 8. It's going to take a long time to get there, but eventually I am. I actually cross all X values, or we can say all real numbers, or I'm just going to say all X values. I guess that's a little bit easier. But what about Y values? What about my range? Well, 1, 2, 3, 4, 5, 6. I'm going to hit 6. These arrows are going up. I'm going to hit 7. I'm going to hit 10. I'm going to hit 100 eventually if my graph was big enough. Question is, if I have a minimum value, am I going to hit everything down here? Well, am I ever going to hit -1? No. Am I ever going to hit -2? No. The lowest we're ever going to go is 0. The Y values that we hit on my graph, how do they compare to 0? Well, they're not less than 0. Less than 0 would be down here. The Y values we hit are greater than or equal to 0. I promise domain and range is something you're going to continue to explore in every class from here on out. So then I want to jump to C. Please do me a favor, go ahead and pause. See if you can graph C based on transformations and play fill in the blanks, and then you can verify and walk through it with me once you unpause the video. Okay, so that 5 is inside parentheses. Inside parentheses is left and right. Now remember, left and right is backwards. Since it is +5, that actually means I'm going to go to the left 5 units. Now this -6 is on the outside. That's going to be my K value. And up and down makes sense because it's a minus. I am going to go down 6. So I'm going to go left 5 from the origin, 1, 2, 3, 4, 5, and I'm going to go down 6. 1, 2, 3, 4, 5, 6. I'm going to place a point. We don't have any A values. I don't need to worry about wide and skinny. So I'm going to go up 1, over 1 in both directions to kind of guide my parabola. And there we go. We have a parabola. So where's the vertex? Well, my vertex, I went to the left 5, so -5. I went down 6, so -6. My vertex is at -5, -6. And again, this is vertex form because there's the -6, really easy to see, but that -5 is right here. It's just opposite of what the sign in the equation actually happens to be. Okay, where's my axis of symmetry? Think of axis as a line of symmetry. We've already talked about parabolas being symmetric. If I could cut this parabola in half, that dotted line would be that line of symmetry. If I could fold my paper in half, which I could, right across there, the two sides of my parabola should meet up perfectly. My line of symmetry, how do I identify that? You could say, oh, it's in the middle. It is. But if we wanted to assign a number, we could do that as well. Take a look at where that dotted line actually goes through. Does it go through the x-axis or y-axis? Well, it goes through the x-axis. So we're going to say the line of symmetry is at x equals, well, what number does it go through? Literally, what number is that? Now, my x-axis isn't labeled, but I can count it. 1, 2, 3, 4, 5 in the negative direction. My axis of symmetry is x equals -5. And that's no coincidence that it is the exact same number as the vertex, because just like the line of symmetry, the axis of symmetry is down the middle, the vertex is the middle point. So the vertex is the middle point, the axis of symmetry is the middle line, if you will. Now, I'm not even going to worry about domain. Yeah, I guess we might as well go through it. Domain, x values, range, y values. Cool part is domain of parabolas, and I'm only talking parabolas, quadratics. This does not go for any graph you will ever see in your life. Coffee break. But the domain is all x values or all real numbers. Again, if these arrows, these arrows indicate that I'm going to keep going very, very slowly. I'm going off to the left and right. I will eventually hit any x value there is. But what about range? Well, eventually I'll go up here to, what is this, 4. Eventually I'll hit 10. These arrows are pointing up. But I will eventually not hit negative 10 because my graph stops here, which is down here at 6. My y values stop at negative 6. Now they're at negative 6, so I have an equal bar. The question is, are my y values greater than negative 6 or are they less than? It's pretty easy to see with a x value, or excuse me, a y value of negative 5, a y value of negative 2, y value of 1. My y values are greater than or equal to negative 6. Now, the last one that I want to go through with you guys, we're going to jump over to page 273, and we are going to do E. We are going to do E again. Do me a favor, pause it, see if you can get that graph in there, and see if you can fill in the blanks, and then you can unpause the video to verify. So here we go. Things that have happened. Negative 2. Ooh, it's negative, so that means I'm going to flip, and if I work out twice as much, I'm going to get skinnier. Inside the parentheses is my left and right. Remember, left and right are backwards from what you think it is. So a negative is going to be to the right 4. And on the outside, my k values, up and down makes sense. I'm going to go up 1. So we're going to get that graphed. First thing we're going to graph is the vertex. Best part of vertex form is, again, that vertex is right there in the equation. So from the origin, I'm going to go right 4, 1, 2, 3, 4, and I am going to go up 1. 1, 2, 3, 4, up 1. I'm going to make a point. There's my vertex. My vertex is always identified by H and K. Now, my graph needs to flip, so I know it's going to go down. Now, typically, and I'm going to switch to a different colored pen, typically, if I had not adjusted my wide skinny, my next points would be here. Again, perfect triangle with the vertex. But I know that we need to be skinnier by a factor of 2. Now, again, if you want to know exactly how that 2 is going to affect the points, verify in your calculator or let me know. I'll run through it with you. But as long as you know it's skinnier than these points, as long as you draw in something skinnier, I am A-okay. There's my skinnier graph. Now we're going to play fill in the blanks. Does this graph have a maximum or a minimum? Well, I can tell now that it's flipped over. That vertex is its highest point or its maximum. And the highest my graph goes is a y value of 1. It goes up to 1. The axis of symmetry is that line that cuts me through the middle. The vertex is the middle point. The line or axis of symmetry is the middle line. It literally goes through the x-axis, so x equals, and it goes through an x value of 4. And now the vertex of the graph is 4 over 1 up. Now take a look at that. No coincidence here. That x value, yes, this is part of my vertex, but it also happens to represent my axis of symmetry. And that y value happens to represent my, in this case, maximum. If my graph had a minimum, that y value would represent my minimum. It's always going to represent your max or min. So here's what I'm going to ask you to do. Feel free to finish up B and D. We did not do that. B and D, you will see those in my answer key that I am going to post a PDF of on Canvas. I realize this was a long video. I will have office hours this afternoon. You can go ahead and read Canvas to see how you can get a hold of me if you want to ask me questions in person. You're always welcome to email me. So ask questions, rewatch the video. Give B and D a try. That's just practice. You can verify those answers with the answer key that is on Canvas. And then you will notice when you're on Canvas, you do have a little bit of homework. From page 274, you're going to do number 4. That's it, number 4. It's got 3 parts. You're going to sketch me 3 graphs and identify 3, each of the vertices. Vertices is the plural of vertex, the vertex for each graph. And then you will also see you have another activity that's going to link you out to Desmos. You'll click on it in Canvas and it's going to link you to a matching. If you have any questions about that, please, again, email me or I will see you in my live office hours. Have a fantastic rest of your day, ladies and gents.